All righty. Good morning, everybody. Can you see me? I don't know if you can.
Yes, thank you.
Awesome. All right. People are still popping in, so we'll just wait for a few seconds. But um, yeah, welcome to PChem 2. Let me remove that annoying background. Better. So how everybody's doing? Had a restful uh, 6 weeks. Yeah, I think it was 6 weeks break, right? I'm glad it happened. We needed it. So there's, let's see, how many people here right now? Probably most everybody. I think we're missing probably just one person. All right. So um, I actually haven't done a Zoom live class yet. Most of my lectures have been sort of pre-recorded or face to face. So this is my first go at it. So oh, I'm hearing feedback. That's okay. So if anything's weird or whatever, just let me know because I don't know what you're looking at right now. Um, I assume my face, but I have no idea. Awesome. All right. So for today's sort of lecture, oh, wanted to mention, since this is sort of my first Zoom lecture, I'm not sure how people usually ask questions. So you can either just unmute yourself and ask questions. That's fine. You can ask questions in the chat. Hopefully, I see it in the middle of everything. That's all good. If you want to use the raise hand features, that's also good. I don't know. It's all fair game. We'll see what works as we go along during the semester. Sounds good? I I see some of you shaking heads. That's good. The rest of you have your cameras off. All right. So for today, let's see what we're going to talk about. Just briefly, some introductions. Uh, yeah, my handwriting on my laptop's not good. We're going to talk about the course and just sort of go over some topics in the syllabus briefly before jumping into classical mechanics. However, you keep notes are entirely up to you. Um, yeah, I'm less inclined to share the notes that I do make because I want everybody to sort of write something down as we're going over this course. For this course, these are sort of what my you can't even see that what my lecture notes look like, right? You can do whatever, but I'm not gonna necessarily share these with you because I want you to sort of make your own notes. All right, so off to for some introductions. So many of you, I've seen many of you around campus. So many of you have probably seen me around. Maybe you know what I'm called. But I'm Dr. Zabe Chalai, and it's a weird name. I know many of you probably haven't seen a name like this before. Uh, I don't know anybody. I know one other person with this name online who's more famous than me. So Zabe here is pronounced like the end of pizza, right? Za and then Bay. And July here is pronounced like the month of July, just with a sort of chu lai. That's me. Um, in case you're curious, I did my undergrad at CUNY, that's the City University of New York, in chemistry, of course. I got my PhD at Penn State. Whoops, that's Penn State. There we go. And that was in chemistry, but with a focus on theoretical and computational chemistry, specifically for nanoparticles. And then I did my postdoc at University of Minnesota, again on theoretical and computational chemistry, focusing on something called quantum embedding. So really teaching this course, which is physical chemistry 2, or really should be called quantum chemistry. That's sort of my area of expertise, right? I've studied a lot of quantum systems and different quantum methodologies. So that's who I am, and I could sort of barely see some of your faces, but I see all of your names. Hopefully on Thursday when we meet face to face, I get to sort of meet and know more of you. Uh, yeah. All right. So let's talk a bit about. If you have questions, just let me know. Right? Because I can ramble on like all professors in the world. Let's talk about the course a little bit. So as I mentioned, you're all seeing my screen, right? My like laptop screen. Okay, cool. So this is PChem 2, or quantum chemistry, as I mentioned. It's an upper level course, so it's not going to be easy. Um, Generally, when people refer to physical chemistry, it's really just this chemistry of, well, you see, this is the problem with chemistry. Certain chemistries, like organic, it's obvious. You're studying molecules with carbon, hydrogen, oxygen, and so on. Um, Physical chemistry, as the name implies, simply means the really it's the physics of chemical systems, right? And if I'm not mistaken, many of you have done sort of PChem 1 that focuses on thermodynamics. PChem 2 sort of focuses on quantum chemistry. And the other major sort of area of physical chemistry is statistical mechanics, or StatMech, which we don't teach at an undergraduate level because it's hella complicated. Um, but in this PChem 2, we're going to focus on quantum chemistry, and many of you have heard of that phrase before. Quantum here, of course, means sort of quantity. Quantity, because it comes from, I think, Latin. So quantum chemistry, as the name implies, deals with very, very small quantities of things. Really, um, well, we'll get into exactly how it came about and stuff like that. But quantum chemistry just means somehow when we get to the smallest scales of things, things occur in sort of discrete quantities. So as I mentioned, quantum chemistry and really quantum mechanics in general is very, very popular, um, or very, you've heard, I'm sure everybody's heard something about it in pop culture. Um, Maybe it's something that's correct, maybe it's not, but we've all heard something about quantum mechanics or quantum chemistry either through movies or documentaries or all of that good stuff. So what I want to do right now is just take a couple of minutes. I'll put you into small rooms, and I want you to share with each other one thing that you've heard about either quantum chemistry or quantum mechanics from pop culture, or that you've learned yourself through watching a documentary or something. So let me see if I can uh, even remember how to do that. So I'll put you in small rooms and share one thing about quantum chemistry that you know from pop culture, and just we'll take 2 to 3 minutes for that. And here we go. Hello. Um, oh, are people coming back? I'll close the rooms. All right, welcome back. So let's hear some of those ideas. We'll start with room one. Anybody could be like, unmute yourself and shout out what some of the things you talked about. And you don't have to repeat. Well, you could repeat things that have been said already.
I think one of the main things we talked about was how quantum stuff doesn't really behave like we normally think about things. Like we're used to, when we look at something and we like, I hold up my phone and say it moves from here to there, you know, that's what we think physically, but stuff doesn't work like that on a quantum level.
Awesome. Anything else?
Non-intuitive is the word I'm looking for.
Non-intuitive. If I spell that correctly. This is not an English class. Spelling this is not graded. Actually, I don't know. I might grade spelling. Anything else from room one?
Like when Newtonian physics just starts to fail to explain
Newtonian
observations.
physics fails. Yep. All right, let's hear from. Is physics singular or plural? Doesn't matter. As I said, it's not an English class. What about room two? What do we? Some of the things we know about quantum mechanics from pop culture or just documentaries and stuff.
We were gonna kind of say same thing that the last group said, but I guess I've heard this thing called quantum entanglement or something
Awesome.
where I guess like two different is it electrons or something like they behave well. I guess you can predict how one behaves because of how the first one does. So like they've been using that to like study things like teleportation and stuff like that, which is
Yep.
pretty
Awesome.
crazy.
We will touch on hopefully just the basics of quantum entanglement through this course. We're not going to go into that into more detail, into like very very much detail. But yep, quantum entanglement is a thing. Anything else from group two? Group three. What's some of the things that you talked about?
Yeah, for our group, this is kind of like a new topic. All of us don't have much information on quantum mechanics. We knew it had to do with the motion of really small particles, kind of how they work. But other than that, we're kind of in the dark on this.
Yep. Awesome. How about group four? If I'm looking off to this direction, it's because that's where your faces are. I should. Doesn't matter. Um, group four.
We were kind of in the same boat as the last group, but we talked about how it was in Marvel movies and it's in rocket science too.
Mm-hmm. You said rocket science, right? Yeah. Quantum mechanics in Marvel movies is a. Let's not get started down that road. Rabbit hole. Any other thoughts from group four? Cool, cool. How about group five?
I think the main thing that was brought up in group 5 was the weirdness of like the three polarizer experiment. So because basically when you have two polarizers that are at 90 degrees from each other, you get no light through, but when you put a third polarizer between them, you get light through all of a sudden. And that has to do with them acting like a wave instead of a particle.
Oh yeah, we're gonna talk about something similar to that. Are we gonna talk about? See, in this course, we don't focus too much on light, quantum, or light mechanics, light wave mechanics, because the three polarizer experiment, as he's mentioning, has to do with light, and light behaves as a wave, and so you know, the effect of that three polarizer experiment could be understood from just wave mechanics, but the same thing can also happen for electrons, which is awesome. Yeah, I don't know if we're gonna actually touch on that experiment though in this class. I could work it in. Anything else from group 5?
Not really.
Cool, cool. So for the most part, we've sort of heard something about quantum mechanics. We know a lot about, sort of Newtonian physics fails, things don't behave normally, or things are non-intuitive. And for many people, it's sort of a very new topic, though people use it in movies and pop culture a lot. Really, what this course, I hope to achieve from this course, is sort of demystify that topic a little bit. How many of you, if you're not like visible, you can like type in chat, but how many of you are planning to sort of go on to, I don't know, grad school or do something with physical chemistry? I saw one hand, and I don't know how many people whose cameras are off. You're raising your hand, but the answer is probably very, very little, right? A very small percentage of you are actually going to do physical chemistry for a career, maybe. I don't know. And so what hopefully, on top of like all the things that you're expected to do for a regular class, what I'm expecting is that you take something away from this class that 10 years from now, when you're having some random conversation with somebody in a bar or whatever, and they bring up something about quantum mechanics that is clearly wrong, you can contribute something to that conversation and still sort of remember all of the basics and all of the sort of fundamentals of the theory. So hopefully we get to that point where you can talk about these things conversationally, um, on top of doing all the fancy math and all that's involved. Sounds good? All right, so let's just briefly go over, hopefully you've all seen the syllabus. Let me see if I have no idea what you're looking at, but maybe here. The syllabus is sort of here. Close, there we go. Hopefully you've all looked at the syllabus, and you're most of you are probably seniors, I would guess, so you don't need me to go over the syllabus with you. Just a few things though. Our textbook is PChem, second edition by David Ball. I was told that you guys used this for PChem 1, so you should all have it, which is great. You need calculator, access to internet, all that good stuff. Here's your course learning objectives. I'm not going to go over that with you, but pretty much some of the things that we're going to learn, well, all the things that we're going to learn are in there. What I do want to talk about is the structure. This is a hybrid format, and as you're all here, so you know what's going on. On Tuesdays, we're going to meet via Zoom using this very link, and on Thursdays, we're going to meet in UIndy Hall B. We have that hall reserved for both Tuesdays and Thursdays, and based off of some of your backgrounds, I see that some of you are on campus already. Honestly, I would prefer to do both face-to-face instead of Zoom. There's a whole lot of technical mumbo jumbo going into just doing a Zoom lecture. But I know at least one person who has a conflict during this time, and so that's why I'm recording it as well. So on Tuesday, the Tuesday Zoom lectures, I'm going to record and also put a link on ACE. exams are going to be during the Thursday face-to-face time period, and homework, I'm going to talk about that in just a second. But basically, that's the format. If you're in quarantine, you can read that, and hopefully, you don't have to switch to an online-only format. Course policies, all that nonsense. For communication, we're going to use two different formats. We're going to use ACE forums for what we're going to call sort of public communication. That's anything that the answer to which could benefit more than just you. Like asking a question specifically about the upcoming exam or something. Like the answer to that, maybe everybody would benefit from. So you would ask these in ACE forums, and to do that, you just sort of come here. There's forums. I put some topics up there that we can work with. However, if you have like a personal communication to me, like, I don't know, you're sick or something, you don't want everybody to know that necessarily. You'll send me those messages on using the messages sort of feature in ACE. Again, you're all seniors. You probably use these many times. Just letting you know, those are sort of my preferred way. I think the university in general just wants us to use ACE for like communications rather than email. Not sure why, but we're going to listen to what the people say. Your grades are all standard stuff. We're going to have 3 exams and then a final exam. That's sort of the bulk of your grade. And then we don't really have homework, but we have this Jupyter notebooks thing. So many of you are probably asking, well, what is that Jupyter notebook thing? What does that even mean? Well, you see, the thing is with quantum chemistry is a lot of it, as many of you have rightly pointed out, is non-intuitive, right? So it's hard to really visualize what's happening when we write numbers or write equations on a page. And so Jupyter notebooks is just they're just a short sort of programming language way to visualize equations, visualize things happening in nice sort of graphs and stuff. It uses Python programming language. I don't know if any of you have used that, but you don't have to be an expert in anything, programming language or otherwise, to do these. So let me just give you a quick look at what I mean by that. So if you go to lessons, I usually will put up here sort of your reading assignments. So for example, today I've asked you to read these 3 sections before class. I don't know if you did or not, but you know, I asked you to read these 3. Thursday, I'm going to ask you to read, and I'll update these on a week-to-week basis. Here's the link for the Jupyter notebook, and they're each going to be due 2 weeks after they're assigned. So for if we go all the way here, I give you the due date for each of them. And what they are, you'll just click this launch binder thing. And what they are is just a little, well, coding notebook to help you visualize things. This binder loading thing will take a while. What it does is it takes the notebook that I coded and is trying to build all the necessary behind the scenes stuff so that you can run it on your computer, and then it loads up and it just looks like this, right? It has all of the instructions that you need, and you sort of, it starts very, very simple, how to do things, and then it gets more and more complex. This is just the first one. And I'm building these from scratch. So if you find anything that's confusing or anything like that, let me know. I set up a sort of forum section right here for Jupyter Notebooks Q&A that we can sort of all help each other navigate and use these Jupyter Notebooks. But like I said, they use Python programming language. So anytime you see these sort of in whatever, that's a Python programming language. But the notebook itself will go through step by step how you use the programming language. Does that make sense? So programming is going to be, I think, I might be biased because I'm a computational chemist, but it's going to be increasingly valuable skill set to have going forward, because so many things with the, you know, increasing computational speeds and all that, like so many things in the future are going to be programming based. You know, we're going to be coding things long before we run experiments in labs and stuff like that. And even in sort of regular old work settings, knowing some bit of programming will become increasingly helpful, I think. So if you've never done any coding, this is a great place to start. You're not going to be able to code some fancy AI that's going to take over the world using what we do here. But, you know, it's a good start. So if you have questions about these, you know, just let me know. But in red, they'll have the specific exercises within this notebook that I'll be grading. And if we go back to lessons, each one of you would have like a specific equation or variable to try when you're working with this notebook. So if you look at this PDF that I linked to, which somehow is not loading, here we go. There are values for variables A, B, and C within the notebook, and those are the numbers you should use. If your name's not on here, let me know, but I think everybody should be on there. You can work together, but for example, Salem, if I'm saying your name correctly, you should use a value of 3 for A and 4 for B and 7 for C whenever you're like making your graph or whatever. And so yeah, you can work together, but you need to use these specific values. And then when you're done with it, all you do is file, download as HTML, and we'll download a copy of the entire thing, and then you'll just submit it by the due date on the assignments tab. Does that sound good? Again, I'm sure you'll have lots of questions because this is going to be entirely new for you. Where are we? So we can ask them here, and hopefully if one of you know the answer, just answer it. If not, I can help answer it. And let me know how this works, because I still have like we see in the syllabus, there's 7 of those due every 2 weeks, and I haven't really made any beyond the first one. So I want to see how that goes. So you can get started on it early and let me know how that goes. But that's essentially our homework. It's a way to sort of visualize the complex equations that we use in class. But for the first one, it's really to get you familiar with the tool of a Jupyter notebook. So there's exams and final exam, that's all standard. Yeah, and you can read the rest of stuff. It's all boilerplate that's in every syllabus. And
I have
here's,
I have a
go
quick
ahead.
question on the final. Is it written by you, or do we have to take an ACS final this
That's a
semester?
good question that I haven't decided on yet. Mostly because I don't know what's on the the ACS final. I've heard from Dr. Stires Barnett is comprehensive in terms, it contains PChem 1 and 2. And I don't know if I want to do that because PChem 1 is a whole semester ago, and most of you are probably going to forget most of it by the end of this semester. If I do go that route, I will wait much less than the 100 that I show here if I go that route.
Okay, thank you.
However, for my own exam, it'll be like 100 points. It's like if I use the ACS exam, it might be worth like 50 points or something. We'll work on that. Because I know we tend to forget things pretty quickly. Sounds good?
Yep, thank you.
Awesome. So yeah, here are dates for all the things. Here are sort of the reading assignments, but this could change as we go along the semester. I just went through and sort of figured out how much stuff we might be able to get done in a lecture period. But you know, I could be wildly wrong. But generally from the book, as you'll notice, we hope to get through chapters 9, 10, 11, 12. We'll skip 13. 13 is about symmetries, and nobody cares about symmetries except the inorganic people. And then we'll do 14 and 15. In case you're wondering what that sort of looks like, let's see. So in chapter 9, we're basically just going to look at classical mechanics, right? That's where everything starts. And we're going to go through this course the same way that somebody discovering quantum mechanics might be going through it. We're going to start with what we know, which is classical mechanics, and then we'll continue with sort of how it fails. And then in chapter 10, okay, now that we know that classical mechanics has failed, we need to develop something new. And so we're going to look at how we develop quantum mechanics, and then talk about the simplest example of quantum mechanics, which is something called a particle in a box. That's not chapter 9, that's chapter 10. All right, so chapter 11 will then move on to something more complex than just a particle in a box, and we'll talk about vibrations. And really, when we talk about vibrations, we'll use something called the harmonic oscillator. Again, these words might sound foreign to you, and that's okay. But hopefully by the end of the course, you'll know what they mean. But we'll move on to vibrations, and we'll also talk about rotations. And to talk about rotations, we'll use something called a rigid rotor. See, the problem with quantum mechanics is the equations are very, very complex to solve. And so particle in a box, harmonic oscillator, and rigid rotor are very sort of simplified version of how molecules work. And after we talked about rigid rotor, we can then go ahead and look at just the simplest atom in existence, the hydrogen atom. For chapter 12, we're going to look at spin. So now we're going to start talking about two electrons, not spin. That doesn't make sense. Electron spin. And then we're going to move on to an approximate solution. So far we would have looked at simple solutions, the one underlined, and then hydrogen atom. And then for things that are more complex than hydrogen atom, we actually don't know how to solve it. So we're going to look at approximate solutions. And in chapter 14, because we're skipping chapter 13, we're going to look at rotational spectroscopy. So 14 and 15, we're going to start looking at spectroscopy. That's the understanding how molecules behave with light. So we're going to look at rotational spectroscopy. We're going to look at vibrational spectroscopy. And then in chapter 15, we're going to look at electronic spectroscopy. And we'll talk more about what each of those entails. But finally, we'll end chapter 15 by talking about lasers. And hopefully that is essentially sort of a map of what the course should look like. If some of these words sound foreign to you, that's entirely fine. We'll know what they mean by the end of the course. Any questions on that?
Quick question about exams. I know last semester they were open note. Will that continue with this semester? I know DSB said in the past when he's taught the course it was open note, but.
So that's a very interesting question, because a lot of quantum mechanics is doing complex math, which it doesn't matter what notes you have in front of you. If you don't know to do the thing, you don't know to do the thing. So from that perspective, it could be open note. But then I want a lot of the questions to be sort of, not a lot, some of the questions to be essay type. Because remember, one of my goals for you is so that you can have conversations about quantum mechanics. And so that involves not math on page, but rather, can you explain this concept to somebody who hasn't heard of this concept? And that would require essay type answers. And those, you can certainly write something out and then copy exactly that in the exam. So open notes wouldn't work for that. So it's something I will think about and let you know. But
Thank
that's
you.
good. All right. So I did not think that going through the introduction would have taken this long. But let me just sort of wrap up with some expectations. I don't know why I wrote expectations. So being a difficult course as it is, and I don't know how you learn, each of you specifically, everybody might learn a different way, but I usually find that if I miss a class, especially an hour and a half lecture about some complex topic, you come back the next day and you're like, oh, where are we? What is all this fancy alien hieroglyphics? So the expectation really is that you attend all classes. Otherwise, you could fall behind really quickly. If you really have to miss a class, you can let me know, but make sure you sort of get the notes from one of your coworkers. You don't want to sort of fall behind. So if you have to miss a class, make sure you get the notes as quickly as you can. The expectation is also that you read the reading assignments. Let me know if you can't read my handwriting. I barely can sometimes. Before coming to class, so that we're at least familiar with some of the words and terminologies before sort of we talk about it in lecture. So they're usually not that long. This book is a really simple, is not the right word, um, but it doesn't go into very much detail about anything, which is maybe good, maybe bad. But it makes the reading assignments before class pretty straightforward. There's not, and by reading assignments, I don't mean you have to practice the math or anything. We can do that in class, but just make sure you read some of the ideas and concepts before coming to class. There's also end of chapter questions. So I would like you to practice end of chapter questions after we've done a lecture about something, so that you just practice the concepts for yourself. Whether you do one question or all the questions is up to you. Just do them until you feel comfortable with the specific type of problem. And if you have any questions about those, just let me know. We will go over some questions in class, but it's impossible for us to go over enough example or enough problems for you to become comfortable in it during the course of a lecture, because of how fast things move in a course like this. So that's why the end of chapter questions I think are important. And then I would say start working on the Jupyter notebooks early. You have 2 weeks to complete them, but don't start them the night before, because who knows what issues you may run into. Like I haven't, this is the first time I'm making them. I haven't stress test them. I probably haven't even thought of like something that I take for granted. Like, oh, I know how to do this in a Jupyter notebook. So I thought, I might have taken it for granted, but you might not know how to do it. And the instructions are not in there. So start them early so that you can, hit all the bugs early, so we can iron out all the kinks and bugs, before it's due. And finally, I would like you to ask lots of questions. None of this is easy necessarily. Hopefully, my aim is to make it easy, but none of this is easy, and none of it is intuitive, as some of you have rightly pointed out. And so, ask lots of questions. If some weird math step happened that you've never seen before, ask about it. My aim is to break everything down as easy as possible, but again, a step I might take for granted, you might be like, oh wait, how do you go from that step to that step? So let me know, ask questions as I'm working, so that I can clarify steps. I think you're all seniors, you know the drill, but that's probably one of the best ways that we can learn. Like, don't wait until after the fact to ask questions. Sounds good? All righty. So that's a 40-minute introduction that I did not intend on, but yeah, that's an introduction to our course. Now, as I mentioned in our little sort of course outline here, we're going to start with classical mechanics, right? And it's always interesting to me that a course on quantum mechanics start with classical mechanics. And if I were to talk about classical mechanics, this would be an entire course by itself. How many of you have taken a classical mechanics course? Nobody. Do they even have one in this university? In physics, maybe? I don't know. But yeah, I don't know. I don't think any of you are physics majors, so you probably wouldn't have taken a classical mechanics course. People study this for entire semesters, right? There's, I study a few classical mechanics course in grad school too, and they're not easy. So how am I supposed to, in a lecture or less, talk about the entirety of classical mechanics and have you understand what classical mechanics is before we go into quantum mechanics? Well, let's try. So classical mechanics, and we're not going to talk about all aspects of classical mechanics, but really by the end of the sort of this mini lecture, hopefully, so let's write some of the objectives. hopefully I like using different colors. You're able to identify the similarities and differences between Newton's, who is sort of the grandfather of classical mechanics, Lagrange's, and Hamilton's equations of motion, sometimes shortened to EOM, equation of motion, and use these EOMs in simple problems. So that's all we're going to do. Just learn about the 3 different types of equations of motions and use them in some simple cases. Nothing complex. Although, like I said, this might be an entire class. This lecture might be an entire class on classical mechanics at a 100 level or something. All right. So anybody knows what this classical mechanics refer to? You can shout it out. You can type it out in chat if you don't want to speak. That's all good. Anyone? Classical
motion regarding to larger bodies,
motion.
like larger as in bigger than like a particle.
Mm-hmm. Yeah. Certainly, it's what it applies to. More specifically, classical mechanics, the word classical usually refers to like ancient, old things. I don't know if ancient's the right word. Like classical music, right? It's old music. I can't think of another example. Classical then in this sense is really just old mechanics. Mechanics here is study of motion. You're right, right? And classical here just means old. So it's the old way of studying motions of things. Really, classical mechanics refers to all physics, let's say before 1900, before around 1900 CE. So what this sort of generally refers to would be, for example, Newtonian, which somebody mentioned earlier, Newtonian mechanics. Another thing that's usually grouped with classical mechanics is electromagnetism, right? That's the study of electricity and magnetism. And, there's a lot of other stuff. Who cares about that? It's classical, it's old. It's not what we're here to study necessarily. But all old physics before 1900 refers to classical mechanics. And sort of modern physics refers to pretty much things after 1900, but there are two big components of modern physics. One is, of course, quantum mechanics that we're going to study in this class. And the other one is, does anyone know? What's the other big sort of field of physics after 1900? Very famous.
Is it Einstein or?
Yeah, it's relativity. So those are the 2 major areas of modern physics. There's others, but I'm not a physicist and not a physics class either. So, but most of sort of physics and theories of how things work are grouped into this idea of classical mechanics or classical physics and modern physics. And quantum mechanics, of course, fall under the modern physics category. You've all done thermodynamics. Probably would fall under, it is classical mechanics because a lot of those ideas have been developed, 1700s, 1800s. I don't know, dates are not, this is not a history class. And so they're really like old ideas that we still use and they're still very useful, but they're old ideas. This is probably one of your first class. I could be wrong. I don't know all the classes you've taken, where you actually learn some science developed over the last 100 years, maybe. Most of organic, well, some inorganic, lots of inorganic are new. Biochemistry is sort of new, but those fields existed, 100 plus years ago, but quantum mechanics did not. Although we are coming up on a 100-year anniversary pretty soon, which is cool. So that is what classical mechanics is. It's sort of just old physics. Now, the basis, and like I said, the granddaddy of classical mechanics is Newtonian mechanics. And we all know Newton's 3 laws, right? Well, I assume we do. If not, it would be nice to read them. But in specifically, let's focus on Newton's second law. Does anybody remember what Newton's second law is? Second law of motion. So Newton's second law of motion.
That defines force equals mass times acceleration.
Yeah, that's Newton's second law. F equals ma. So F here is the force, m is the mass, and a is the acceleration. Does acceleration have 2 L's or 1? Nobody knows. I mean, somebody knows, not me. So that's Newton's second law. I mean, in words, it's a lot more complex. It's like a body at rest stays at rest, or a body in motion. No, that's the first law. I'm trying to remember what it is. It might just be something like the acceleration of a body is directly proportional to the force applied to it. Something like that. Doesn't matter. We just care about what the equation looks like. It's F equals ma. That's Newton's second law. Now, we've used this equation since high school, maybe. At least I did. I'm sure you guys did too. And we know that acceleration, so here's where we're going to get into some calculus, but simple calculus. We know that acceleration is the change in velocity with time, right? V here is velocity. I'll highlight it. So V is velocity. And we know that velocity is the change with position over time, where x is position. Again, we could use x for position, we could use y for position, we can use z for position. But what that really means then is acceleration is the second derivative of position with time. And let me know if any of these terminologies don't make sense. I think one of the prerequisites for this course is calculus. But if you're not familiar with these terms, let me know. But this is the second derivative. So these are all time derivatives, right? So really what we could do is write something, we can rewrite that equation this way. Force is equal to mass times the second derivative of position with time. That's the same as Newton's second law. Now, let's just do a little bit of side notation here, and let's look at time derivatives. Because this is going to come up a lot, and we don't want to write this over and over again because we're lazy people. You will learn that scientists, theorists are very lazy, and equations can look very, very complex very quickly. And so we want to simplify how we write things. So let's say you have some function of time. Time is a variable. Doesn't matter what that function is, right? Let's say you want to take the time derivative of this function, right? That's usually how you write it, or you can write it df dt. Does this seem familiar to people? All right. Well, we're going to simplify that even further, and we're going to just write f with a dot over it. And that dot will signify a time derivative. How many of you have seen this before? One person, maybe? Okay,
Just in the
so at
reading.
least, sorry?
Just in the reading.
Just in the reading. Okay, great. So if I'm going too slow, let me know then, because I can speed up. So the second time derivative then of the same function, or we can write it as the second derivative of f with respect to t. Really, we're going to write that as f with two dots. So this is the first time derivative, and this will be the second time derivative. Just to simplify our stuff, because we don't want to keep writing this whole complex thing. We can just write f with a double dot over it. So if we come back over here, we could write this even easier as f is equal to m times x with a double dot over it, right? It's all the same thing. So just way to write fancy math.
Is that strictly for time?
Yes, the dot is only for time. People have other ways to write derivatives, first and second derivatives and more, when it's not respect to time. If you want to learn, actually, I can show you. If you want to do, let's say it's f with respect to x and you want to do d dx of f, right? People write usually df dx. You can actually just write f prime. And then the prime implies it's with respect to x. If it's more than just x, if it's x and y and z and whatever, then you can't really use that. But the dots are specifically for time. The little tick apostrophe is for other derivatives. And this, you can continue this for third derivative and fourth derivative and all that fancy goodness. But we don't care about that. And we're not going to look further than second derivative, at least not in this section. All right.
In the textbook, it gave us like terms like x with one dot over it and then squared. Is that the same as x with two dots over it, or is that referring to something different?
X with one dot over it squared is different. So remember what x with one dot over means. It's df dt, right? So f, okay, let's do x. X dot is the same as dx dt, right? So x dot squared will be dx dt squared. Whereas x double dot is d squared x dt squared. They mean different things. You can come up with some value of x where these two things are the same, but that's not always going to be true. Sounds good? Cool. All right. So here we're using x, but it doesn't have to be x. It could be y, it could be z. And this is only for things moving in one direction, x, right? If you have something more complicated, like moving in x, y, or z direction, I don't know, you're a spaceship moving in three-dimensional space, you might write something like this. There'll be x dot plus y, x double dot plus y double dot plus z double dot for stuff moving in both, in all directions. But as I mentioned earlier, we're just, because this is not going to be a comprehensive classical mechanics course, we're going to keep things simple for one dimension only. Imagine a ball bouncing up and down, or a car moving back and forth between one city, or somebody running a race or something. We're not looking at people doing crazy curved circuits. All right, so we have Newton's second law, which is the basis of all classical mechanics, right? And we have it written in a way that we can use easily with the m dot double dot. All right, where do we go from here? Well, let's say that we're now going to apply this to some system. And again, I'm sure you've done examples of this, might have been a while, but let's say you have, for an object m, we call the object, no, we don't care what we call the object, with mass m. So we have some object, it has mass m, right? That's just a symbol for what the mass is. The force it feels due to gravity while on Earth's surface is, the force is minus mg, where g is the acceleration due to gravity. The negative sign means the force points downwards, right? So positive, in this example, positive is going to mean upwards, negative is going to mean downwards. Find the velocity of the object and it tells us that the initial velocity is v0 and the initial position is, we'll call it z0. So we're going to go on the z-axis, not the x-axis. How many of you have seen a problem like this? I don't know, high school math? Yeah. Might have been a while though. So let's just go, I'll go over this with you, just for those of you who see this and make, oh shoot, it's been a while. So we know, we have Newton's equations of motion. F is equal to m times x double dot, right? They give us F is minus mg, and they give us m, the mass, which is just m. So we know that F is equal to m times x double dot. Well, let's use z double dot because it's in the z direction. We know F, it tells us that F is minus m times g, right? So we replace F with what F should be. We know what m is, it's just m, right? And then we have z double dot. So we take Newton's second law, and what we did is consider the specific force. And we end up with this equation. The question is, find the velocity of the object, right? So we know that velocity is the first time derivative, right? So we have here the second time derivative, z double dot. So we just need to find the first time derivative. So I'm going to expand this. Instead of the double dot, I'm just going to write it out. So we have minus mg is equal to m times the second derivative of z with respect to time. We see immediately that the masses cancel out. So the second derivative of z with respect to time is equal to minus g. Right? Now, this is a differential equation, and we have the second derivative, and we want to find the first derivative. So all we need to do is integrate, right? So we integrate this thing with respect to time on the left-hand side, and then we integrate this thing with respect to time on the right-hand side. Does that make sense? So if you integrate a second derivative, you get a first derivative, right? That's just how derivatives and integrations work. So you end up with the first derivative of z with respect to time on the left-hand side. And on the right-hand side, what's the integral of minus g with respect to t? Does anybody remember their calculus?
Negative gt.
Yeah, that's it. Negative gt plus some constant c, right?
Would the
Yeah.
constant here be v naught?
Right. So the constant is always your initial starting condition. So we'll write v naught, and this is your initial velocity. And this here is your velocity. So your velocity is equal to minus gt plus some initial velocity. And that's it. That is the initial velocity of the object. Let's add one more to this. Let's also find the find the position of the object. So we have the velocity. Let's find the position. So the position is just z, right? Z tells you where something is on the z-axis. So we want to find z. Let me know if you have questions. I don't know if I'm going too fast or too slow. But to find z, we just got to integrate this again, right? dt with respect to time. And then we integrate everything on the right-hand side as well. So the integral of minus gt plus v0 with respect to time. On the left-hand side, we integrate. We just get z. On the right-hand side, what's the integral of minus gt with respect to t? So t becomes t squared, right? So it's minus gt squared, but we have to divide by that new 2. So we get that. Does that make sense? The v0 becomes v0 times t. And there is also a new constant of integration, but this will be the initial position. So we're solving for position. So this becomes z0. Some people usually put a little time parentheses there to show that this function is a function of time. So this here is the velocity function. This here is the position function. Now, I want us to pause and just think about what just happened. All we did was we started with Newton's second law. That's where everything starts with in classical mechanics, more or less. We had a specific problem that gave us a specific force, right? All we did then is solve Newton's equation with that specific force, and we can get a velocity function and a position function. And this position function, once we know some initial velocity and some initial position, can tell us everything we want to know about that particle, right? If you want to know what this particle was doing 4 billion years ago, you enter negative 4 billion into that time, and you get what the particle was 4 billion years ago. If you want to know what this particle is going to do 10 billion years in the future, you plug in 10 billion for time, and you get 10 billion years in the future. If you want to know what the particle is doing right now, you plug in 0 for time, and you get what the particle is doing right now. Does that make sense? So this is Newtonian mechanics. You know something about the particle, maybe some initial velocity, some initial position, right? V0 and Z0. You know the force acting on it. You can know anything about the particle at any time. That's the beauty of classical mechanics. And it was sort of this idea that the world was living in back in the 1800s, when people were like, oh, all we got to know then is enough information about maybe some initial velocity or some initial position, and we can know everything about the universe. We can just plug in Newtonian mechanics. However, classical mechanics is more than just Newtonian mechanics. I talked about 2 other forms, right? I talked about, where are we? Lagrange's formalism and Hamilton's equations of motion. So this is Newton's equation of motion, and it works really, really well for straight line stuff. And it works really, really well when you know the force, because F is equal to ma, you just plug in for the force. But in most cases, we don't know the force, right? A lot of cases we don't know the force, but what we do know is the energy of a particle. So let's look at Lagrange's equation of motion. Equation of motion. Again, everything is built off of Newton's equation of motion, just in different form, because he is essentially the leader in the field. Lagrange's equation of motion, I'm just going to write it out because it's not one necessarily that you've studied. Everybody knows F is equal to ma, but not everybody knows the others. So in Lagrange's equation of motion, it says this. It looks weird, I know, but it says the time derivative of the derivative of this L with respect, the partial derivative with respect to x dot, and this little symbol here is partial derivative. I'm assuming you've all done multivariable calculus. Yeah, no? Okay. It's kind of looks like a D except it's swirly. Big D means sort of regular old derivative. Little squirrely D means partial derivative. For practical purposes, they're not really different, but that's what it is. And this guy here, L, is called the Lagrangian. Lagrangian. Okay. And you might be wondering, well, what is the Lagrangian? The Lagrangian is really just the kinetic energy minus the potential energy. So K here will be kinetic energy. And V here will be the potential energy. Like I said, for Newton's law, things move in straight lines, and it works really well when you know the force. But in many situations, you don't know the force, you know the energy. And so Lagrangian was like, well, let's rewrite Newton's law in terms of energy. And so he defined the energy. And when you work out Newton's law with the energy, this is what the equation looks like up here. So this is what that equation is going to look like. You don't have to memorize this equation. And most equations in this course, you're not going to have to memorize. But just know what it looks like and how it works. For example, well, let's look at kinetic energy. Kinetic energy, who remembers the formula for kinetic energy?
Half mv squared.
Yep, half mv squared. But remember, we're using this dot and double dot. So v was x dot. So it's half x dot squared. This is where the x dot squared is not the same as x double dot. So it's half mv squared. You can remove the parentheses if you want. So that's kinetic energy. And then potential energy, well, that can be different, right? Because the potential energy can depend on, maybe it's gravitational potential energy or electrostatic, it doesn't matter. But if you know, so in Lagrange's formalism, all you need to know is the potential energy and you can solve the problem. In Newton's equation, all you needed to know was the force and you could solve the problem. Does that make sense? Let's look at an example. And let's not look at gravity again. Let's just look at something a little bit more simple. Let's just prove by examining Lagrange's equation of motion that his equation is identical to Newton's. Because I told you that he got this by just rewriting Newton's equation in a different way using energy instead of force. But why should you take my word for it? Let's just prove it for ourselves. All right. So we know that the Lagrangian is kinetic energy plus the potential energy. And we know that the kinetic energy is half mv squared or x dot squared, right? Because that's velocity, plus some potential. And the potential always depends on x, or x and y, or x and y and z, right? Like the potential energy, that's the definition of a potential energy. Potential energy depends on position, not motion, right? Yeah. Does that sound familiar? So the potential energy is always going to depend on position, x. I can write that. Depends on position. Holy crap, time is moving really fast. I'm not going to get even half done that I wanted today. Am I going too slowly? Okay. No, that's all good. That's all good. All right. So we know the Lagrangian, and we wrote it out for some general potential. We don't know what the potential is, but our job is to prove that it's the same as Newton's equation. So let's try to solve this equation up here, and we'll do the left-hand side and the right-hand side separately, right? So let's do the right-hand side because it looks easier.
Real
All right.
quick, is the
Yep.
Lagrangian kinetic energy plus potential or minus? You have it
Minus.
written two different ways.
Yeah, no, it's minus. Sorry
Thanks.
about that. Yep, it's minus. The Hamiltonian, which we'll learn about next, is just kinetic plus potential. All right. So let's solve the right-hand side of Lagrange's equation of motion because it looks simpler. And it's the partial derivative of FL with respect to x. So that's the partial derivative of L with respect to x. And so if this is L, it's going to be partial derivative with respect to x of half mx dot squared plus v times x. Everybody with me? Okay. Derivative with respect to x of this first guy here is 0 because this first thing doesn't have x in it. It has x dot. X dot is not the same as x. So it goes to 0. Right? And then the second term, this has x in it, but we don't know what the function is. It's some random function. So we end up with the partial derivative of v with respect to x. So that's what the right-hand side comes out to. This is equal to this. Doesn't really do us any good. Let's look at the left-hand side. I thought we could get away with the right-hand side because it looked easier. So the left-hand side of Lagrange's equation tells us to first take the partial derivative of L with respect to x dot, and then take the time derivative of that. So let's do step 1. We have L is equal to half mx dot squared plus some random function of x. The first step is we take the partial derivative of L with respect to x dot, right? That's what it says right here. And so this has x dot. So if you what's the derivative of x squared with respect to x?
2x.
It's just 2x. So the derivative of x dot squared with respect to x dot is just 2x dot. So 2x dot, so it'll be 2 times a half times m times x dot, right? Does everybody see that? And then the half and the 2 will just cancel out. So we end up with m times x dot. And then, why do I keep writing plus? The Lagrangian is minus. Sorry, Lagrangian is minus. And the derivative of v with respect to x dot is 0 because v doesn't have x dot in it. It just has x. Okay, so we got that first part. Let's look at the second part. We now need to take the time derivative of what we just solved. So the time derivative of the partial derivative with respect to x dot will now be the time derivative of what we're left with here, which is just m times x dot. Yeah? And we know that time derivative is, you just add another dot. So this becomes mx double dot. Is this starting to resemble Newton's equation now? Remember, Newton's equation is F is equal to mx double dot, which is exactly what we have there. So it means that this here is some expression of the force. So all Lagrange did is he wrote this here is the force, and this here is kind of like MA. He just took Newton's equation, and instead of using force, he used kinetic minus potential energy, and he came up with this equation. And people are like, oh, wow, Lagrange is smart, but he's not really that smart. Actually, he's very smart. But I'm hoping that you can see how these complex things we can also sort of derive if we just sort of wanted to. Does that make sense? So let's look at the two differences. So Newton's equation of motion works for straight lines and when we know the force. Right? Lagrange's equation of motion, it doesn't really matter if you're moving in straight lines or curved lines. Works whenever we know the kinetic and potential energies. They both have their uses. You don't always know the force, or you don't always know the energy, but whenever you know one or the other, you can figure out anything about the particle. They're all the same equations, just written differently. And then in the last 2 minutes, can I do this in 2 minutes? No, I cannot. I did not want this to last this long, but my intro lasted long. So, you know what? I'm gonna wait. Our class is supposed to end at 10:40, right? 10:50, sorry. Yeah. Okay. You know what? I'm gonna end here. You've learned enough for one day. We're gonna pick this up on Thursday, where we're gonna finish up with some examples. We're gonna look at Hamilton's equation of motion, and that should wrap up the 3 different types of equation of motions we talked about. So far, we talked about 2. On Thursday, we're gonna finish up the Hamilton's equation, and then we're gonna look at some cases where these classical mechanics stuff fail. Any questions about what we've done today? There's some equations in the back end of chapter that involves these Hamilton's equation and Lagrange's equation and Newton's equation. If you want to practice, if you feel like you want to get in the groove of doing these little differential equations and integration equations, again, if you're rusty, I would definitely start practicing. And if you want to start looking at the Jupyter notebook, you can follow the link under like lessons and ACE. Otherwise, I will see you all on Thursday at 9:30 a.m. in UIndy Hall B.